Using the torque, derive the relationship for the engine power dissipated in the bearing. Okay, so we have our torque. So we need to know what is the engine power dissipated. So what does this mean? As I said earlier, when you are spinning, okay, when you are actually spinning the shaft. So this piece is the shaft. So when you are spinning this, right, you have a torque force spinning these things, and the power dissipated is when you have the torque itself. The power is lost when you're trying to resist the frictional force, trying to resist the frictional force against the turning of the torque itself. So the power is dissipated through this manner. So if you have to take in other assumptions, in other words, there will be a certain frictional force trying to oppose the torque, right? The torque is turning in this direction. So nonetheless, you will have a certain friction due to the wall, surface of the wall over here, right? So I hope I didn't confuse you, or hope I explained it clearly. So we have to get power from torque. So the knowing U is equals to the this U, okay, is equals to U. What I mean is taking back this one. This one is the velocity profile if you to enlarge. This is the plate, and this is the thing, right? Then you have the velocity profile, and then you have uy cross y, and this is the velocity of the plate, or the turning of the velocity of the shaft turning. So knowing u is equals to u, in this case we're talking about this contacting point over here, this whole point throughout the whole, what I mean is this point throughout the whole shaft. Okay, so this is the point where it is turning, right? This is the point where the torque is being applied throughout. So therefore, the linear velocity, okay, is equals to omega, angular velocity, multiplied by r first. Okay, but what we are doing is actually to create an equation to have a power equation, because the power is in terms of angular velocity times force. Okay, so we have to change in terms of angular velocity first. So as you can see, our linear velocity is actually the v. So this is actually linear velocity. So imagine this is the shaft, this whole piece is the shaft, and then you are turning. Okay, you're turning with a certain angle, and then the velocity, it's from, you translate from here to here, you have a certain angle, right? So it is much related to this angle over here. So this is what it means. Okay, this angle is equal to this angle over here. So linear velocity, when you talk about linear velocity analysis, is that you assume that the particle at here is one piece, and when it's here it may be moving in this direction, when it is here it is moving in this direction. So you're taking in consideration of all the motion. At every point the particle is moving in linear. Okay, so I don't know whether you may understand. How do I say it? So linear velocity, okay, I think you understand what I mean. Linear velocity is just a velocity that is straight line. Angular velocity, it's turning, is a rotational angular velocity. I don't know what I explained. But nonetheless, if you don't understand, it's okay. It's just an equation. So the linear velocity, as I show you, is over here, and this is also linear velocity. So the particle at this point is this linear velocity, or the particle at this point is this linear velocity. So at any point, this linear velocity is equals to the angular velocity multiplied by the radius. Okay, so therefore, because we want to find in terms, the purpose of us is to find in terms of angular velocity so that we can multiply by force. right? So we just bring this from this r downwards, so you have v over r, right? And then this velocity is actually the velocity of the plate that is moving. Okay, the plate is moving at a velocity u. It's a linear velocity. If you look at the shaft, this is the shaft. So at this point, maybe I should draw over here. At this point, it is linear velocity, right? This is the plate of the. This is the velocity of the plate, and then the fluid profile. It's right. So this is what I mean. So this is the linear velocity, and therefore, we can set v is equals to u, since v is the linear velocity. So, um, so I just bring the r downwards. That's all. Yeah, bring this r downwards. So you have, you can see the trend now. So to find power, angular velocity is 1 over s. Okay, what does it mean? Angular velocity itself, it's this linear velocity is meter per second divided by meter, which is radius, right? And therefore, if you cancel, you have 1 over s. So this is angular velocity times the force, which is the top force, which we found earlier, Newton meter. Okay, and therefore we have the power Newton meter per second. Newton meter or joules, energy per second. The energy per second that the energy dissipated throughout the fluid, trying to move the fluid, is this equation over here. And how we get this equation? We just sub in the top. Okay, this is the top. Well, this is the UR. So what I do is actually to bring this U over here. Okay, so this is why U is over here, and then R to cancel away this R squared, right? So when you leave R squared divided by R, you have R. Because this whole piece is multiplication, right? This is top. This whole thing is top, okay? And then this is UR. So just simply multiplying it over here, and then creating the R. So I'll just rewrite. So the only changes in the R and this U over here. That's all, right? And therefore I can rearrange. What I need to rearrange is I multiply this portion into each of this thing, because they are addition, right? So this one multiplied by U divided by A, so we will have U square, right? This is U times U equals to U square. The rest is 2 pi R nu. Okay, this is in dynamic viscosity nu. 2 pi R L nu. Yeah, the same thing. Okay, I didn't cheat you. They're exactly the same. Okay, and then U square over A, right? And then plus 2 pi R L nu again. In this case, okay, 2 pi R L only. So this is 2 pi R L over here. And then this nu is being cancelled away by this denominator nu, right? So they are cancelled, and we are left with del P del X A, right? And U itself. So maybe I should rewrite. So when I multiply in this portion over here into here, okay, this is what I have. This portion is this portion over here, and then this is simply this. So as you can see, the common term is nu, so I can cancel. So what I have is 2 pi RL. This is 2 pi RL, and then this is actually A, and U, del P del X. So we have derived the power from the top. Okay, so this power is dissipated to move the fluid, because the fluid itself has a certain shear stress caused by the fluid, caused by the frictional wall from the bearing. So just to recap, okay, we derive our horizontal velocity component U, and then we use this U to derive the shear stress. Okay, the shear stress is due to the moving of the shaft, the turning of the shaft, and the friction caused by the bearing itself. The bearing is stagnant, right? But it generates certain frictional force, preventing the shaft from turning. Okay, I hope you get what I mean. And then using this shear stress, we find the torque, because the lesser the friction, okay, caused by the bearing, the lesser the friction caused by this bearing over here, the velocity, the faster the fluid can flow, right? So you need to generate lesser torque. So this is what it means, and therefore um, the power required will be lesser to move this shaft, to rotate this shaft, I would say. So next video I'll just derive an expression for the volume flow rate Q of the oil between the two plates. So what it means I'll just explain later, so see you in the next video.